there, Energy 301 students. It is time to learn about using test statistics. You know, in this whole module of the course, what we're learning about is how to make inferences based on data. We're using inferential statistics. We have learned about things like how to write hypotheses, a null hypothesis and an alternative hypothesis, which are exhaustive yet mutually exclusive, so that if you could prove that one hypothesis was false, you would know for sure that the other one was true. Now, the problem is we can't ever really prove that. We have to actually work with the observations that we have, and we try to infer which of these hypotheses are going to be true and which of them are going to be false. And in order to do that, our tool is going to be test statistics. So that's where we're going with this lecture today. Now, these inferential statistics and test statistics, I like the word test statistics better than inferential, are quite different than what we learned about when we talked about statistics back in a couple modules ago when we did the descriptive statistics. I mean, back in the descriptive statistics module, we talked about quantities like average, or sample standard deviation and sample variance, or correlation, or the various regression statistics like the slope of the regression line and its y-intercept and things like that. And all those statistics were, to a greater or lesser extent, familiar. They were things that you see in your day-to-day life or in scholarly work or even on by watching Monday Night Football. I mean, they'll talk about the average, yards gained and things like that. They are all, one thing that they have in common is that all of these statistics were estimators of parameters. There was a real property of the system, like its mean, which we can't actually get. We can't actually know what the mean electrical load on the grid is going to be. We can't know what the mean power to be generated by this wind turbine is going to be. We can't know what the mean temperature at that location is going to be, but we can make estimators of it with statistics like the average. And one thing that all of these statistics, these descriptive statistics, also had in common was that they were based on the data. Okay? We collected observations, let's be more correct, we took samples, and then we used the values of those random variables to compute these statistics. Well, what we want now is more statistics. We want some new statistics that will help us make inferences, to make decisions, particularly about whether or not we can reject our null hypothesis. Remember, we wrote two hypotheses. We want to reject one of them as a way, we want to figure out if we can reject the null one so that we can accept the alternative one. Now let's go back to our example that we've our thought process, our thought experiment, if you will, that we have been doing throughout this module. This was this idea about could we compare, could we determine whether or not there was a difference between the mean height of a Creighton student and the mean height of a student at UNO. And remember, we wrote two hypotheses associated with that idea. We had this hypothesis that was our null hypothesis, H naught. And our null hypothesis was that the mean height of a Creighton student, the mean, the real parameter, the real property of the system of Creighton students, that its mean was equal to the mean of the heights of UNO students. That was our null hypothesis. And our alternative hypothesis was that the means of the mean heights of the Creighton students and the mean heights of the UNO students were not equal to each other. Notice that those two hypotheses are exhaustive. There's no other possibility. Either they're equal or they're not equal. And notice that they are mutually exclusive. They can't both be true and they can't both be false. One has to be true and one has to be false. Now, we had been taking, in previous lectures, we talked about taking samples of Creighton students, which is fraught with problems, remember? I mean, you have to be very careful that your samples are representative and all that good stuff. But you could then compute the average height of a Creighton student. Average, it's a statistic. And we use that symbol Z bar CU and Z bar UNO to indicate that. Sorry, my dog just came over here to say hello. Anyway, now, I didn't think about it when I made those PowerPoints, and I didn't want to go back once I did realize it and reinvent the wheel here. But Z was actually a terrible choice of a symbol to use when we were making those charts and stuff like that, because we're going to be using Z for something else. So from this point forward, I'm going to switch and just use Y instead, okay? So Y is going to be our measure of heights of students, and Y bar will be our measure of the average heights of the students, and so on. So let's think about, from a statistical point of view, what our experiment here looks like, rather. Sorry, excuse me here. Well, let's take the Creighton situation first. What we're going to do is we're going to take some observations of the heights of Creighton students. So we will have some number of observations. I'm going to call that number NCU. That'll be our number of Creighton students that we observed. And every observation will be Y, the height. I'm going to use YCU to mean it's a Creighton student, comma I. So like there'll be the zero with the first observation, the second observation, all the way up to the NCU observation of students at Creighton. And we could add all those Creighton students up, and we could divide by the NCU, the number of the Creighton students, and we could get the average height of Creighton students in that sample, Y bar CU. Now, like we talked about in previous lectures, this has all the problems of an average. It doesn't mean, this is just the average of the students we measured. It's just the average of the students we measured at that time. I mean, some of those students are growing. It's an average. It has all the problems and all the good things about being an average. And we could do the same thing for the students at UNO. We could take some observation of the heights of students at UNO. There could be N UNO observations. That would be the number of observations that we're taking of students at UNO. And each one of those students would, his observation would be called YUNO, comma I, where like I would go from 1 to N UNO. And we could add them all up and divide by N UNO and come up with the average, which we'll call Y bar UNO. So we would now have an average of this little sample. Again, it has all the good things and all the bad things about being an average. It's just an average. In addition, well, those observations that we took, both of Creighton students and of UNO students, well, there's some scatter. It isn't like all N of those students were exactly the same height at Creighton, or all of them N were the same height at UNO. There was some scatter. We need a measure of the variance or the standard deviation or something inside of that group. Well, it turns out that a good measure to use is the sample variance, which we remember from the descriptive statistics chapter was S squared. So there'll be some, and you could go back and look at, I don't feel like putting those equations in right now, but you could go back and look at what is the sample variance of the height equation, and you could compute the sample variance for UNO students, call that S squared UNO, and you could compute the sample variance of the Creighton students and call that S squared CU. Both of those would be measures then. Maybe all of the heights of students at Creighton tend to be all about the same, and maybe all the heights at students at UNO tend to be more scattered for whatever reason, I don't know. Anyway, you would need to know those two pieces of information. We're going to need them in order to compute our inferential statistic. So what would it look like? I mean, we wrote these two hypotheses. One hypothesis was that the two means were equal to each other, and one hypothesis was that the means were not equal to each other. What we're going to do here is we're going to sort of set up a little trap. We're going to say, what would it look like if the null hypothesis was true? And then we're going to find out, does our data show that that's just not very likely? Okay? Is there something about our data that says, boy, for the null hypothesis to be true, this would be really strange. Something odd happened in our observations, therefore we say that we don't really like that null hypothesis, we're going to reject it. I mean, we're not going to use words like not really like, we're going to come up with statistical tests and so on. So let's kind of build from this idea. What if the null hypothesis were true? What can we figure out based on the observations we took? What kind of inferential statistic could we compute based on the observations that we took that would lead us to wonder, is this null hypothesis right or not? In order to do that in this particular case, well, if our null hypothesis is that the means are equal to each other, one thing you could do is you could rearrange that. Instead of saying that means are equal to each other, you could rewrite the null hypothesis as, what if the mean, you're saying that the mean height at Creighton, mu CU, minus the mean height at UNO, mu UNO, is equal to 0. Okay, we just sort of rearranged it. In other words, we could say that the difference between the two is 0. That's equivalent there, okay? If the null hypothesis is true, this is true as well. Okay? Well, if I knew the means, we would be able to solve that, right? The problem is we don't know the means. I mean, if I knew the means, we wouldn't have an experiment in the first place, right? If I knew what the mean height at Creighton was, if I knew what the mean height at UNO was, we wouldn't have an experiment. Okay, but we do have averages, and they are estimators of the mean. So let's kind of approximate this process here by taking the difference between the averages. So let's actually compute like y bar CU, the average height of Creighton students in our sample, minus y bar UNO, the average height of UNO students in our sample. That's an interesting thing because, see, here's the deal. Even if that null hypothesis is true, I'm not sure yet whether I think it is or I think it's not, but even if it's true that these two are equal to each other and that that difference should be 0, the difference of the averages is not going to be 0. Because, I mean, even if null hypothesis is true, that difference between those two averages won't be 0, because it's just a statistic. It is just a property of the students I happen to measure that time. Okay? If I pulled N students from Creighton and took their average height, and I pulled N students from UNO and they took their average height and took the difference, it's not going to be, even if the real mean is 0, the difference isn't going to be exactly 0 because one group to another is going to just vary just by random chance. We happen to get a few more taller students this time. We happen to sample a few smaller students this time or whatever. Rather, that difference, that y bar CU minus y bar UNO, has a distribution. I mean, if I conducted that experiment 1,000 times, like what we talked about in the last lecture, yeah, if the null hypothesis is true, most of the time that difference would be really small. If, again, we're working in the hypothesis idea here that the null hypothesis is true. If that null hypothesis is true, most of the time that I take, and therefore the two groups have the same height, most of the time that I take an average of the Creighton students and an average of the UNO students, that difference is going to be small. And we get kind of this hump in the distribution right around the difference being equal to 0. But sometimes the difference is not that small, just by dumb chance. Maybe a bunch of tall students happen to be in my sample for Creighton, or maybe a bunch of short students just happen to be in my sample for UNO. That happens. And if you look at the distribution here, you can see it doesn't happen a lot, but sometimes it does happen. So there's sort of a bell-shaped curve to this distribution of y bar CU minus y bar UNO if we're still believing in that null hypothesis. If we believe in that null hypothesis, if that's true, then the distribution of y bar CU minus y bar UNO should follow this little bell curve. When I actually take my sample of students from Creighton and my students from UNO and compute that difference, it should be consistent with this. It should be most likely that the difference is near 0 and really unlikely that it's way out in the tails of these distributions where the difference was large. So for example, let's say I actually took that sample and I measured the mean height of Creighton students in some sample and I measured the mean height of UNO students in some sample and I got a difference of 0.25 centimeters. Okay, if I look at this curve here, 0.25 centimeters, that's really close to the hump of the distribution of this variable if we're assuming the null hypothesis is right. Okay, so if I look at this curve here, 0.25, that's a pretty common possibility on this histogram here. That's a pretty typical observation, excuse me, typical difference according to this distribution, assuming that the null hypothesis is true. So this evidence that I gathered, these observations of heights of Creighton students and these observations of heights of UNO students is making it really hard to reject the null hypothesis. Since the result that I got, namely that this difference is really small, it's pretty consistent and pretty likely according to the null hypothesis. It's pretty much right near the hump of the distribution. Most of the time my average is going to be about that size. My difference between the averages. Okay? On the other hand, let's say I measured the average height of Creighton students and the average height of UNO students, took the difference, and got that the difference was 17 centimeters. That's a big difference. 17 centimeters of a difference, I mean, from one person to another, 17 centimeters of difference is no huge deal. But if you have a average, you took, there's some average, there's some tall people, some short people, and you took the average, and you got the difference between the two groups of 17 centimeters, according to this distribution anyway, that would be really weird. I mean, my graph only even goes up to a difference of 2.5 centimeters. 17 centimeters is way off in the tail of this distribution. It's practically never would happen. If, under the null hypothesis, a difference of finding that the average of the groups were this different of 17 centimeters is really, really unlikely. Well, that sounds like a contradiction then. It makes it really easy to reject that null hypothesis, doesn't it? Since that result is actually incredibly unlikely if the null hypothesis is true. If that difference is really that big in our averages, yeah, you know what? Maybe there is no difference between Creighton's heights and UNO's heights, but we just happen to get most of the members of the Creighton basketball team in our sample. But the sample distribution here is showing us that's actually almost never going to happen. And so we could reject the null hypothesis, and then we could accept the alternative hypothesis. So remembering then, what we want is a statistic that can tell us this, a statistic that can help us make decisions about whether or not we can reject the null hypothesis. We need some kind of statistic that tells me, how weird is this? How weird is this difference between these two means in this case, between these two averages here? So what I'm going to show you here is a test statistic for the difference between two means. As you can see by looking at that equation already, it's a fairly horrible looking equation. And I'm not expecting you to memorize it or even use it, okay? The purpose of this here is I'm trying to show you that this exists, okay? This is the test statistic, it's Z, that we use when we are comparing two means. If our which is, by the way, obviously a very common thing we would want to do in science or engineering or whatever. We'd want to know, is this wind turbine producing more power than that wind turbine? We're comparing the mean wind power at this station versus that station. Or comparing the mean electrical load on weekdays versus weekends or something like that. I mean, comparing two means is probably the most common thing we're going to be doing with statistics like this. So it's not totally irrelevant to have this kind of information in front of us. But as it happens, this particular test statistic or inferential statistic, Z, it only applies when we are trying to compare two means. All right, we'll learn that there's lots of these kinds of test statistics out there. Okay, first off, notice it's a statistic. It is a function of the data. It has things in it like y bar and s squared and n, all of which have to do with the sample that we took. Z is not a property of the system the way a parameter would be. Z is not a property of Creighton students or a property of UNO students. It's a property, it's a statistic that we derived based on the samples that we took. It's a ratio. Notice what's in the numerator of the ratio. It's just the difference between the two averages. So you computed your average height of a Creighton student, you computed your average height of the UNO students in the sample, and you took the difference. Right off the bat, look what that means. The smaller that difference of those averages were, the smaller, the closer to zero that Z is going to be. And the bigger the difference between those two groups are, the farther from zero Z is going to be. Okay? So the numerator is just the difference between the averages. Now that denominator is kind of a mess. Strictly speaking, that denominator actually turns out to be the standard deviation of the difference between the heights of pairs of students. One being from Creighton and one from being from UNO. But I recognize you would not immediately have seen that. But the fact is the denominator there is a measure of like the variability of these groups. If all the Creighton students are all about the same height, and you know, like there was an admission, part of admission was you had to be taller than this line to come to Creighton, and not as tall as this line, then Creighton's standard deviation or variance or whatever would be smaller, and UNO's would be bigger. That just has to be in this particular test statistic. Now, the people who derived this Z test statistic did something amazing. This has one really great property that is kind of the model as to how we make test statistics and inferential statistics work. If the null hypothesis is true, notice I have that super duper underlined right there. If that null hypothesis is true, which is the assumption we're working on right now, Z will be distributed according to the so-called standard normal distribution. That's the familiar bell curve. Okay? It doesn't matter what the distribution of Creighton students' heights are. It does not matter what the distribution of UNO students' heights are. It doesn't matter what... It can be proven that Z will be distributed according to the standard normal curve, which looks a little bit like what I have over there in the top left corner right now. We'll zoom in just a little bit. But that bell-shaped curve is what Z will look like, or its distribution. If you made a histogram of Z, it would be distributed according to that bell curve. That's brilliant, because the bell curve is mathematically a mess, but can be done. We can solve for the properties about this bell curve. This bell curve is like a type of histogram or whatever. It is showing us that values of Z near zero are the most likely if the null hypothesis is true, and the values way out there in the tails of the curve are very unlikely if the null hypothesis is true. So here's the deal. If we get a value of z based on, we compute this z statistic, this inferential statistic based on the heights of Creighton students and the heights of UNO students in our sample. If we compute that value of z and we get a value of z that's way out in the tails of the distribution where it's incredibly unlikely, I mean, really? We just pulled these students at random off the campuses and we got something that like breaks this distribution? Apparently, this distribution is not right. I mean, we took a sample and we ended up with something so incredibly unlikely. It's probably the case then that our z is not distributed like this, right? If we got some goofy low value of z, or a super duper high value of z way out there in the tails of the distribution, well, the only assumption we made to get to this point was that the null hypothesis is true. And we broke it. We found out that our sample is incredibly inconsistent with that. We ended up with a value of z that would be so incredibly unlikely that we can go ahead and say that null hypothesis is probably not true. I'm going to reject it. Oh, see how this z statistic is going to help us. We still got a couple steps to go. But the z statistic is going to, because we know how it's distributed, or at least should be distributed if the null hypothesis is true, when we actually get our value of z, if it doesn't look like that, then apparently our null hypothesis is not true, because apparently we're wrong about how that z is distributed. Alright, so I zoomed in really nicely on that standard normal curve right here, and it shows you how for different values of z on the horizontal axis here, you could see how the bell curve tells us that there are, over different ranges of the value of z, different percentages of the time the value of z will fall in there. So like about roughly 19% of the time the value of z will be between 0 and 0.5, and about 15% the value will be between 0.5 and 1, and so on. And if you go way out into the tail of the distribution there, like off to the right in the diagram, you can see that like only 0.1% of the time will the value of z be greater than 3. And so if we compute z and we get a value that's way out there in the tail of the standard normal distribution, that was not a very likely thing to happen. And therefore, the only assumption that we made to get to this point, that the null hypothesis was true, must not be right. Or at least, probably isn't right, or maybe we can at least say we were going to reject the null hypothesis. We're back to this idea of rejecting the null hypothesis. And remember, that means that we end up having, if we've rejected that null hypothesis, we've got to accept the alternative hypothesis. They are exhaustive and they are mutually exclusive. Therefore, if you reject one, you have to accept the other. This is not the same thing as proof, like in the sense of what you learned in 10th grade geometry or something like that. We have not factually proven this, but we have shown that to some confidence level, we'll get to all of that, we have an ability to reject one of the hypotheses, namely the null one, and accept then the other one. Not to say that this couldn't have gone wrong. I mean, that unlikely value of z, let's say we got a value of z bigger than 3. Okay, it's way out there in the tail of the distribution with only like a 0.1. Let's actually put some numbers on this. Let's say my value of z was 2.3. Okay, I've got that location along the horizontal axis there marked with a big arrow. No matter what our value, I mean, 2.3 is pretty far out there into the tail of the distribution, but no matter how far out into the tail of the distribution I happen to be, there is some finite probability that even a bigger value of z could happen just by chance. I indicated that there by shading in that part of the bell curve in red. I mean, some finite probability exists that even bigger values of z could happen. I just might happen to have weird samples. I might just happen to have a really tall sample from Creighton. I might just happen to have a really short sample from UNO. But now I have a way to kind of quantify that. I know what the probability is that I got a sample this weird. It's the integral under this little curve, this bell curve, from where I am z out to the end of the curve, out to the tails of the bell curve. Oh, see, now there's a technique. We can get at what the probability is that we would get a result this strange. Oh, this z statistic has now given us the place that we will be on this bell curve so that we can integrate out and find out what the probability is. It's that area under the curve from z out to the tail. That probability has the rather uninspiring name of P. Okay, it's the p-value of the test, okay? And that probability P can be solved as a really hideous integral. The actual curve that we are integrating here, the equation that we are integrating, is a giant mess. It is not in general something you want to do unless, you know, you really love calculus or something like that. 99.9% of the time what statisticians will be doing is using tables. Either literally like going to the back of their stats textbook and looking up on the tables of these values, or, I mean, in practice, something like Octave or Excel or whatever can give you the values of the percentiles of the z of the standard normal distribution. Typically, though, let's say that we're going to get them off of they're going to correspond to tables in the back of the book of your stats textbook. I didn't think of actually scanning it from your textbook. That would have been much more smart. I just happened to have one of my stats textbook from back, 20 years ago when I took statistics, and I got the values for, and I scanned in right here. And let's just show how this table would work. Let's say I actually took my samples of heights at Creighton and heights at UNO, and I did all the math, and I computed z, and I got a value of z equals 2.81. Okay, on this table here, you look up z. The table is actually kind of weirdly formatted here. You would be going to, the way the table actually works, you go down to 2.8 is the row, and then 0.01 is the column. That's just how this one's formatted. I believe the one in the back of your book is formatted the same way. And so if we went over there and looked up the value for z equals 2.81, and I see I have a mistake on the slide there. It's not negative 2.81, it's just positive 2.81. We could zoom in, because I know that's too small to read, and find out that the probability P is 0.0025. In other words, there's only a 0.25% chance that you would come up with a value of z that, I said small, but it was big. I originally had this as an example using negative. If the null hypothesis were true. Wow. In other words, I computed my value of z, and I got a pretty big value, 2.89, or 2.81 I think is what we used. And if the null hypothesis is true, we now know that's far enough out there in the tail of the distribution that only well less than 1% of the time could that happen by chance. There's only a 0.25% chance that I could just take a sample at Creighton and get a value of z that big. I think we can go ahead and say that is not very likely to happen. And the only assumption we made to get to this point was that the null hypothesis was true. Therefore, apparently, the null hypothesis is not true. We can reject the null hypothesis and therefore accept the alternative hypothesis that the heights of these two groups of students is not the same. Okay? The alternative hypothesis being that the mean of the heights at Creighton is not the same as the mean of the heights of the students at UNO. This distribution is symmetric. We can just flip it and do it if the values of z were negative. Like if we had gotten negative 0.281, we could have just flipped it around and said, okay, this is the probability of getting a value of z this small, this far from zero or farther from zero to the left on the diagram. I originally did have it working through an example of that, but I think that's not the best use of our time. Let's see, for example, what would happen if we had a value of z that was closer to 0. What about a value, we did our math, took our observations, did our math, and found out that our test statistic z for this test of the difference between two means was equal to 1.0. All right, I could take my table of the standard normal distribution, and I could read down to z equals 1.00, and I would get that the p-value of this was 0.1587. In other words, what that's saying is, if the null hypothesis was true, remember this is all built on this idea that the null hypothesis was true, there would be a 15.87% chance that we would see a difference this big or bigger just by chance. If I ran my little experiment of the heights of Creighton students and UNO students 1,000 times, 158 of them would come up this weird or weirder. I would have this big of a difference between the Creighton students and the UNO students just by chance if the mean heights of the two groups were actually the same. I'm not comfortable with that. 15% of the time I could get a result this big. I'm not going to reject my null hypothesis that the two groups actually have the same mean. I'd have seen a difference this big 15% of the time. just by dumb chance. I might be making, that might be my dumb chance right now. I'm not willing to take that big of a risk. I'm not far enough in the tail of the distribution. This is not inconsistent with the idea that these two groups might have the same mean. Therefore, we cannot reject the null hypothesis. This doesn't mean that the null hypothesis is wrong. Is right. It means we can't reject it. We're going to talk more about errors and how this can mislead us on the next lecture. But at this point, we cannot reject the null hypothesis. We can only say the data that we have are not inconsistent with what would have happened if the null hypothesis were true. I can't reject it. So going back to this idea, we have this statistic Z. It's an inferential statistic. It's going to help us make inferences. Remember, inference means that we are reaching conclusions based on observation and reasoning. It's going to help us make inferences about the underlying process. In this case, the process being whether one group or the other is taller. Okay. It's a statistic that's helping us make that decision. We compute the value of Z, and then we use tables to figure out the probability that we would have gotten that value of Z under the null hypothesis. If we get a fairly normal-looking value of Z, like it's fairly near the hump of the distribution, has a moderately high probability of having happened, we can't reject our null hypothesis. The data are consistent with what would have happened if the null hypothesis were true. But if the value of the Z that we get is way out in the tail of the distribution and just too unlikely, our data aren't really consistent with what the null hypothesis is telling us. We reject the null hypothesis, and then we have no choice but to accept the alternative hypothesis. What a neat trick. This has helped us make an inference about the underlying physical processes involved. Neat. And we could have done the same thing. That was a difference between two means type test, which is certainly a very common test in science and engineering. But actually, tests like this have been derived to solve all kinds of problems. That's why textbooks for statistics are so fat. Okay? There are tests that do things like test whether or not a correlation is 0. So like your null hypothesis might be that R is equal to 0, and then your alternative hypothesis is that the R is not 0. Okay? And then there is a test statistic that you can develop, that you can use. You can find it in a stats textbook. It's in your textbook as well. That is, it's a function of the dependent variable and the independent variable. And then the test statistic has some distribution, and you look it up on a table. And if you're too far out into the tail of the test statistics distribution, then apparently the null hypothesis was false. And then therefore, or at least you can reject the null hypothesis, and therefore you accept the alternative hypothesis. There are tests like this that are for finding the slope of a trend line. Okay, there are, this would be like a test to see if beta 1, the slope of a regression line, or the slope of a trend line was equal to 0 or not. So your null hypothesis would be something like H naught beta 1 equals 0, and your alternative hypothesis would be like HA beta 1 is not equal to 0. Sweet. Okay, I can see how that would work. Okay, maybe there would be a test that you wanted to see if the two groups had different variances. Maybe you're thinking that the range of heights at Creighton is smaller than the range of heights at UNO for some reason or whatever. Okay, you could have a null hypothesis where like the variance at Creighton is equal to the variance at UNO, and an alternative hypothesis that the variance at Creighton is not equal to the variance at UNO. And all of these kinds of tests, and literally dozens of others, exist. They're buried in a stats book someplace. It is not productive for us to be sitting here and going through all of these and like showing you the equation and so on like this. And for all of these tests that we would want to do, and all these hypotheses that we would possibly want to test statistics like the Z that we have been seeing in this lecture exist. They have been derived, and for all of them we have derived what their distribution should be. In the case of Z, it was standard normal, but there are, which is the standard bell curve, but there are others. But all of them work the same way in that those are the distributions of that test statistic under the assumption that the null hypothesis is true. Then If you get a weird value of your test statistic that doesn't seem consistent with that hypothesis, that the null with that assumption that the null hypothesis is true, you get to reject the null hypothesis and accept the alternative hypothesis. Now, a lot of those statistical tests that we have been seeing, or that we could, in theory, find in our stats textbook or whatever to test things like correlation or variance or something like that, follow a standard normal distribution like the one that we've been working with today. And some of them follow different distributions, just to kind of give you a sense. Many test statistics follow what is called the student's t-test distribution. The student's t-test distribution is a bell-shaped distribution too, much like standard normal, but it has fatter tails than the standard normal does. It works for especially if their sample size is small. If we took a sample of 10 Creighton students, we'd probably use the student's t-test rather than the standard normal. Whereas if we took a sample of like 100 students, we would switch to using standard normal. But I mean, student's t-test is just, it's another bell-shaped curve. Another type of statistical distribution, another type of distribution that some test statistics, some inferential statistics follow, if the null hypothesis is true, is this so-called chi-squared distribution. And I have some graphs of different chi-squared distributions on the plot here. Chi-squared is different from like bell curve. It kind of has a vaguely bell shape, although it tails off to infinity only in one direction. It's chi-squared test statistics only have one tail, not two tails, the way like a standard normal does or something like that. For many test statistics, they follow what is called the F distribution. F distribution type tests are typically associated with if you're trying to prove hypotheses about ratios. If you wanted to prove that the ratio of women to men at Creighton was different from the ratio of women to men at UNO, the test statistic you would develop would follow the F distribution if the null hypothesis was true. And then you would just find out, okay, my value of F of the test statistic that I got is way out in the tail of the distribution, so then apparently my null hypothesis that the two groups have the same ratio of men to women would be rejected. Okay, we aren't going to do F tests in this class. We're not going to do chi-square tests, but these are terms that you hear in your studies and so on. And so I wanted to at least get you to understand they're all variations on this idea. You've developed a test statistic. Under the null hypothesis, it should be distributed in a certain way, kind of bell-shaped or kind of tailing off to infinity in one direction or whatever, but they're a distribution. And then you look and see, did the value that you got of your test statistic look like something that could happen by chance? If it's near the hump of the distribution, it's fine. It's consistent with the null hypothesis. If it's way on the tail of the distribution, it's not consistent with the null hypothesis. You get to reject the null hypothesis. All of these distributions, standard, normal, student's t-test, what all did I show you? Chi-squared and F have big tables in the back of your textbook, in the back of any stats textbook, on Google, wherever you want to go. All of them, I believe, Octave can give you the values. Most of them, Excel can give you the values if you need them or whatever. But you can get these percentiles and so on for these different distributions. Now, did you notice we didn't have a nifty name like average or sample standard deviation or correlation for this Z statistic? I mean, Z is just sort of a statistic that we use when we are testing the difference between two means. It's pretty specific to that one particular use, and it doesn't even have a name. Okay? We don't call that anything. It's just Z. Okay? Most of these inferential statistics or these test statistics don't actually have a name. The ones that do have names tend to be named after the person who discovered or invented them or whatever. For certain types of tests, for example, you might use what's called the Mann-Whitney Test. Okay, so you would compute the Mann-Whitney statistic, or the Wilcoxon statistic, or the Wronski, I'm not sure. Anyway, I think they do have a name for the Wronskian statistic. But all of these statistics are inferential. I mean, nobody's going to be excited to hear that the Mann-Whitney statistic of this football team's yards per game and this football team's yards per game is this value. That's not so interesting. Okay? But it might be necessary to use a Mann-Whitney statistic in order to prove that this football team gains more yards than that football team does. Okay? So, I mean, by and large, they're not something that just sort of rolls off your tongue. They're not something you're familiar with until you engage more in professional and scholarly work and so on. But all these inferential statistics are just great tools. They are ways to make decisions about things like, can I reject or accept a hypothesis? Can I reject a null hypothesis, which leads me to accept an alternative hypothesis? And all of them are wonderful, and all of them are useful, and all of them have one problem. They can lead us astray. None of these test statistics, inferential statistics, can prove anything. All they can do is help us see how likely it is that the null hypothesis is right. It's up to us, as the scientist, the engineer, the scholar, whatever word you want to use, to decide what that means and make the leap to say, therefore I am rejecting the null hypothesis, or therefore I cannot reject the null hypothesis. But here's the deal. The statistic can lead us astray. It can lead us to make the wrong decision about accepting or rejecting the null hypothesis. This is going to be the whole business of what are called type 1 and type 2 errors, sometimes referred to as false positive and false negative errors. And that's going to be the topic of the next lecture. So next time we're going to learn about the kinds of errors that we can be led to make based on these test statistics. All right. Take a little break, review the PowerPoint. Let me know if you have any questions before you move on to that lecture.